All right, everybody, let's get ready to roll. We have a special visitor today, Dr. Siyuan Wang. And he's visiting us from Boulder, Colorado, where he is a scientist at a NOAA lab in Boulder. He's been around the world, started out in northwest China, which is where he's from, very dry climate, moved to Hong Kong, moved for PhD to Hong Kong, got to be in a humid climate. And then he moved, while he was there, he did a Fulbright at NCAR, and he got to work with, you can tell us more about that, someone at NCAR, back and finished his PhD. Then he ended up as a postdoc at the University of Michigan, and then an NCAR postdoc, and now he's at a NOAA lab there in Boulder. So he's got to experience lots of different climates. And he's going to talk today about two really broad topics, one on marine aerosols and one on wildfires and smoke. And really interested to hear everything about these two topics. So I'll turn it over now to you.
All right, thank you very much for the introduction and also for the opportunity, and I'm really honored to be here. So a little bit about myself. My name is Siyuan Wang, and I am a modeler. I use a variety of different models to understand the physical and chemical processes in the world. I use ranging from global models covering the entire world to very small models. I'll zoom into the small eddies and swirls and fire plumes. And I'm also very interested in cool stuff like machine learning, AI, that kind of stuff. I also like to make, cool animations. And when I'm not working, I like to make stuff. I like to grow stuff. I like, being in Colorado, you're obligated to interact with snow in winter times. And I also like to play music with my friend. All right, so science-wise, today I'm going to cover two broad topics. The first one is the ocean biogeochemistry control on the atmospheric chemistry, and the second one is wildfires. So ocean. So ocean plays a very important role, strongly regulates the climate system, and the ocean emits a wide range of trace gases and aerosols, affecting the self-cleaning capacity of the atmosphere and also the radiative balance. There are lots of previous studies looking at the ocean emissions of dimethyl sulfide, or DMS, and organohalogens and volatile organic compounds coming out of the ocean, as well as marine aerosols. So the production of many of these things in seawater are strongly affected by the ocean, by the biogeochemical processes happening in the surface of seawater. And currently, unfortunately, the ocean biogeochemistry is not fully coupled with atmospheric chemistry in many of the models. So while I was in NCAR, I developed this online air-sea interface for soluble species for the community Earth system model to predict the bidirectional oceanic fluxes of many of the trace gas. In theory, you can use that for any trace gas you want. But basically, this module considers the physical forcing and the physical state and chemical and forcings on both the ocean and the atmosphere side. So the idea is that we can use this to replace the offline prescribed ocean emission approach for many of the compounds, which is, generally speaking, not entirely skillful, and you can't do any feedback using this kind of offline prescribed approach. So this is basically shows how this OASIS module couples ocean biogeochemistry with the atmospheric chemistry. So basically, this model framework has been used in some of our previous applications. But the biggest challenge here is basically the part that is represented by this big red arrow here. The challenge here is that the lack of quantitative and magnetic understanding of the biogeochemical processes in the seawater that would control the production and removal of these things in the seawater. So what can we do? So there are a couple of tricks we can do. For example, in the past decades, there are lots of observations are collected. And for compounds with sufficient observations, we can use machine learning to mimic some of these processes. And here I'm showing two examples that we did in the past. And in theory, these kind of things could be coupled with Earth system models. And in addition to that, for a couple of compounds, the studies have found that, the abiotic photochemical production in seawater actually plays a quite important role. And this is right into the wheelhouse of us chemists. It's very straightforward, relatively speaking. So we have done this for a couple of compounds. Astalate is one of them. I'll talk more about it later. And recently, we're also using this kind of approach to calculate the production of reactive nitrogen species coming out of the ocean. And I want to mention that this work is led by students that I'm currently mentoring. The students currently in Colorado presenting a poster, but I can't be there because I am here. All right, so acetaldehyde. So acetaldehyde is, so today I'm going to talk a little bit more about acetaldehyde, but it's not just about acetaldehyde, it's more about the implication that we can learn from acetaldehyde, more mainly about the reactive carbon in the atmosphere. So for non-chemists in the audience, acetaldehyde is one of the most simplest carbonyl compounds you can find in the environment. It's pretty much everywhere. You can find that in fruit, in coffee, and it's also responsible for hangover after too much alcohol is consumed, because in the body, alcohol is basically first step is oxidizing to acetaldehyde into this. So in the ambient environment, acetaldehyde plays a quite important role because it largely affects long-range transport of NOx from polluted places to the very remote part of the atmosphere. It also plays a very important role in the oxidative capacity of the atmosphere. So we now have observational evidence indicating that acetaldehyde might be a smoking gun for a currently missing reactive carbon source in the atmosphere. So there are a couple of other things about acetaldehyde, because over the past decades of study, we now know its global major sources and sinks reasonably well, emphasize on reasonably. And now it's chemically speaking, so the structure of acetaldehyde is fairly specific, meaning that it's not that easy to make an acetaldehyde from chemical reactions. And lastly, the lifetime of acetaldehyde is about a couple of hours in the atmosphere, so it's fairly short-lived, therefore it's indicative of local chemistry processes. All right, so ocean is, generally speaking, a very big net source of acetaldehyde. So I developed this satellite-based abiotic photochemical production scheme that is for acetaldehyde. It basically calculates the acetaldehyde production from the colored dissolved organic materials. So this model is quite interesting. This is basically, these maps are showing the model calculated acetaldehyde concentration of surface seawater. We can see that it's broadly consistent with limited observations available in the literature. So once we have the concentration, we can dump that into the model and calculate and use that to drive the air-sea exchange process. So on this slide, I'm basically showing some evaluation using the ATOM observation. So ATOM is a NASA large-scale field campaign funded jointly by NASA and NOAA, and this is a global-scale multi-seasonal airborne mission with very comprehensive scientific payload. So I wanted to draw attention first. So these are basically vertical profiles of measurements and models in different oceanic regions. I will, firstly, I would like to draw attention to all these red lines. These are the ChemChem or CSM model with chemistry component in it. This is the model simulation, the base case simulation without ocean emissions. We can see that model drastically underestimating acetaldehyde in the remote atmosphere, pretty much like any other models would do. And then we talked about the abiotic photochemical scheme that I mentioned about previously in the ocean. So once we add that into the model, the blue lines are what the model predicted. We can see that in the marine boundary layer, the model is definitely going towards the correct directions. But the thing is, if you see the marine boundary layers, which is roughly indicated by the red shading here, that the blue lines show very sharp gradient in the marine boundary layer. That is consistent with our understanding because acetaldehyde has a fairly short lifetime, that is about a couple of hours. If you look at the free troposphere, the backward trajectory analysis basically indicates that the free troposphere air has not touched the marine boundary layer for at least a couple of days. They're fairly aged air masses. Therefore, whatever sources you have emitted from the ocean, they can't survive all the way into the free troposphere. So the large discrepancy between the model and measurements in the free troposphere might indicates a missing source of this thing in the free troposphere. Now, if you look at other oxygenated volatile organic compounds measured by other instruments and from previous field campaigns, and they're all consistently underestimated by the models. From a modeling perspective, we know all the models are wrong. But in that kind of very remote places, we don't have other precursors to produce all these things in the first place. So that kind of underestimation in the remote atmosphere turned out to be very interesting. So we speculate there might be currently unaccounted source of acetaldehyde. And because of the short acetaldehyde in the remote atmosphere, we speculate that the missing precursors have to be long-lived. So my go-to response, it gotta be organic aerosols, because organic aerosols have all the organics and also they're relatively longer-lived. So now basically I'm doing a thought experiments based on this steady state assumption because, I'm sorry, I went behind on myself. If we do literary researches, firstly, there are lots of studies looking at the multi-phase chemistry on organics. For example, studies have found that the ozonolysis of organic substrate would actually produce a wide range of small products, including acetaldehyde. In addition, studies have found that the photolysis of organic materials can also produce small carbonyl compounds, including acetaldehyde. So, appears to be a possibility. Now we want to revise the question. Can the particulate organics in the ambient environment explain the observed acetaldehyde in the remote atmosphere? So here I'm basically doing thought experiment testing that basically based on the steady state assumption. The steady state assumption is a reasonable one because acetaldehyde has a fairly short lifetime, so we can assume its sources are roughly balanced by the sinks, and the sinks we can reasonably well constrain its total sink from the observations. Now the first hypothesis I want to test is basically, okay, all the observed acetaldehyde is produced from the heterogeneous ozone uptake. Then we can write down this equation, basically connect the observationally constrained total sink term to the very complicated one on the right-hand side, and all these terms in the wet boxes are essentially the ozone collision rate on aerosols. So we can infer the reactive ozone uptake coefficient on organic aerosols. Now the second hypothesis is basically all the observed acetaldehyde is produced from the photolysis of organic materials. Then we can write down this equation, connects the observationally constrained total source or total sink of the acetaldehyde to the measured organic aerosol concentration. With that, we can infer the organic aerosol photolysis rate or photolysis lifetime. And then here we have to have a yield here. This yield is basically carbon yield. We assume it's 100%. I know it's very absurd, but let's see what happens. So basically this plot shows the vertical distribution of the inferred ozone uptake coefficient using all the observations we collected from the ATOM, the global field campaign. So here I'm chopping off at 3 kilometers, basically limiting my analysis to the free troposphere because I mentioned before that the air masses in the free troposphere are fairly aged, so the impact of primary emissions are very small here. If we look at the pink shaded area, basically in the lower to middle free troposphere, we can see that if we were to explain all the acetaldehyde from the ozonolysis, then the inferred ozone uptake coefficient is generally speaking on the order of 10 to the minus third. If you look at all the gray, I realize you cannot see the shading very well. Basically on this side of the plot are basically the laboratory measured range of the acetaldehyde of the ozone uptake coefficient. It's mostly on the order of 10 to the minus fifth or something like that. But unless if you're talking about like specific compounds with specific structures like alkenes or unsaturated stuff, in that case, the ozone uptake can reach 10 to the minus third or something like that. That is to say, if we were to explain all the acetaldehyde using the ozone uptake, the inferred ozone uptake coefficient is definitely on the very upper end of all the laboratory measured ranges, and usually that kind of level would require certain types of compounds in the condensed phase. So similarly, this plot examines the vertical distribution of the inferred organic aerosol photolysis lifetime. And if we focus again on the lower to middle free troposphere, you can see that the inferred organic aerosol lifetime is about 1 day. That is like 10 times faster than the, generally speaking, the organic aerosol lifetime estimated from previous field studies, which is about 10 days. So that is to say, generally speaking, the organic aerosols are definitely plausible to produce acetaldehyde based on laboratory experiments. But looking at ambient data, it appears that organic aerosols themselves cannot explain all the missing acetaldehyde in the remote troposphere because the level simply is not there. And if you crunch numbers a bit more, the observed acetaldehyde implies a reactive carbon source on the order of 0.1 to 0.7 parts per billion carbon per day in the remote atmosphere that is neither captured by models or observations. This could potentially perturb the oxidative capacity in the remote atmosphere. So what are we missing here? Now I'm going to basically brainstorming and doing literature, trying to see, these are the possible pathways and teasing out my future research direction. In the past, people have been studying photochemical reactions in the gas phase and in the aqueous phase for a very long time. But recent years, people found out, the photochemistry happening in aerosols or at the interface actually turned out to be quite interesting. For example, these studies found that the photolysis and actinic flux are both enhanced inside aerosols and also inside the droplets. And moreover, there are very interesting phenomena can happen at the air-water or aerosol interface. And for example, the solvent effect would drastically reduce the mobility and sometimes lead to very, very different chemical pathways inside the aerosol or in the condensed phase. And in addition to that, at the surface, there might be some very unique properties. For example, many of the compounds are found to be enriched at the surface. And also at the surface, usually the solvent cage effect will be weaker, so some of the reactions might be faster. And also for polarized or ionized compounds at the surface, they might have like very special orientations that would facilitate some of the reactions. So basically, all these unique phenomena at the interface will lead to very unique and interesting photochemistry at the interface. Now, I wanted to draw attention to this very interesting paper. I'm going to put down my modeler hat for a bit and wear my chemist hat for a minute. So a group of French scientists published a paper in 2016 looking at fatty acid photolysis at the interface. So fatty acids are, generally speaking, fairly inert. They don't react with a lot of things in the gas phase or in the aqueous phase, and they don't absorb much radiation as well in the tropospheric tropospheric activity regime. However, what they found is that, when a thin layer of fatty acids is coated at the air-water interface, a number of compounds can be produced when you irradiate sample to the tropospheric relevant radiation levels. And they found a very weak absorption at around 270 nanometers. And if you're a chemist, you know that this is in a much longer wavelength than a typical carboxylic acid would absorb. Very interestingly, just last year, a group of Japanese scientists designed a very, very interesting experiments and proved that, the absorption happened at 270 nanometers are likely a result of a teeny tiny amount of impurities in their sample. So I don't think this necessarily debunks that study, but rather I think in their experience, maybe the impurities are simply acting as photosanitizers. But I want to draw attention to the amount here. Less than 0.1% of impurities or photosynthesizers in their original study eventually drastically changed how chemistry proceeds. So now that we're talking about photosanitizers, there are lots of studies looking at photosynthesized production of many of these kind of small compounds like aldehyde, alkenes, and acids from irradiated organic materials, actually including the saturated long-chain fatty acids. And now, in the meantime, there are lots of studies looking at a dark heterogeneous ozonolysis of natural water samples from coastal waters and from other types of water samples as well, all producing these kind of small compounds. And studies also found that once you release all those products into the gas phase, they can undergo further reactions in the gas phase, producing even smaller or other type of more complicated compounds. Now, how about aerosols? So studies have found that photosanitation reactions can definitely happen on the surface of aqueous aerosols, but with one requirement, that is for surfactants. In fact, what they found is that surfactants are quite important to stabilize the activated state of molecules produced at the surface to promote the further reactions. And guess what? Fatty acids themselves, especially long-chain fatty acids, can actually act as surfactants. And in the meantime, we mentioned before that fatty acids themselves can also undergo this kind of oxidation reactions. So now the sanitizers and fatty acids, they're pretty much everywhere. They're naturally existing seawater, they're existing gas phase as well. They can be coated outside, outside secondary produced aerosols. And for many of the photosynthesizers, they can be produced from the secondary chemistry happening on aqueous aerosols as well. And also this basically this aerosol-based mechanism is also consistent with our previous field-based analysis that the reactive carbon pools in the remote atmosphere has to be sitting in the gas phase. So basically, what's the next step? So we're proposing a combined field and modeling study, and later this year we're going to have a field observation at the small field campaign at the not really small field campaign, but decent sized field campaign at the Scripps Piers at UCSD, and trying to quantify many of the ocean and emission VOCs and primary aerosols from the ocean. And this project was funded by NSF, and I myself am a co-PI, I'm leading the chemistry climate modeling components. So what modeling tools are we going to do we need in order to answer these science questions? So for this project, I'm going to primarily use the community Earth system model, the ChemCam model, basically the model with chemistry components. And in recent years, there are quite a few updates that are very relevant for these to explore these science questions. For example, I have developed a new aqueous-phase scheme on wet aerosols and clouds as well. And also, in addition to that, I have developed another scheme that calculates water uptake due to the organics on particles. And also, I'm also involved in updating the chemistry, the sulfur chemistry in the model. In the sulfur chemistry, people have been studying that for decades, yet every now and then we found something completely new about that. All right, a little bit more about aqueous chemistry. So if you take a dry particle, expose that into ambient levels of moisture, thermodynamics that is likely to exist either in liquid condition or metastable liquid condition. If you further increase the relative humidity beyond the saturation, it may get activated and grow into cloud or fog droplets. So studies have found in the past that the cloud processing actually plays a very important role in the formation of sulfate on the global scale. And recently, people also found that similar kind of reaction, aqueous reaction, can also occur on wetted aerosols that would produce organics and also sulfate as well. For example, this Tao et al. Study indicated that in northern China during the winter haze events, the sulfate formation actually dictated by the chemical reactions happening on wetted aerosols. This kind of process is actually fairly sensitive to pH and transition metals and all the other pollutants you may have. And another study, this study actually using the ground-based long-term oscillation, what they found is that, okay, if you simply plot sulfate as a function of temperature, you have a temperature dependency, and that temperature dependence is drastically, the model is predicting completely wrong temperature dependency for surface sulfate. And the sulfate is drastically underestimated, well, not drastically, sulfate is also underestimated by the model as well. And they actually speculate that this might have something to do with, additional sulfate formation from happening on wetted aerosols that are not widely incorporated in current modeling systems. And if you look at this map here, the circle region showing the southeastern United States, that's where we're seeing the biggest model measurement discrepancy in sulfate. Now the temperature dependency sounds to be a pretty, it's a pretty big deal because we know that in the foreseeable future things are going to warm up pretty soon. If we can't get temperature dependency right, how are we going to make sure that the air quality forecasts that we do in the models are headed towards the right directions? And the small map on the right-hand side are basically showing the fraction of organic water uptake due to a fraction of aerosol water uptake due to organics that I recently implemented into the model. You can also see that again in the Southeast United States, the organics, the water uptake due to organics can account up to 40% of the aerosol uptake. And the rest half is pretty much water uptake due to inorganics. The thing here is that if you don't consider water uptake due to organics, then you're likely underestimating aerosol water by up to 40%, and drastically underestimating all the other things too. So everything is kind of interconnected. Now a little bit more on the aqueous-phase chemistry implementation into the model. So the aqueous-phase chemistry is actually not widely implemented in most 3D models simply because they are very expensive. The gas phase chemistry is expensive enough, the aqueous-phase chemistry especially so. So in most of the modeling system, they're either parameterized as heterogeneous surface chemistry or solved separately in a crude Uralian type of solvers. The problem now is the latter approach is that firstly, it's completely decoupled from chemistry, and secondly, it's not scale aware and also may have some stability issues. So recently, I developed a module that handles the explicit phase transfer and aqueous-phase chemistry for the community Earth system model. This offers quite a few advantages. Firstly, it's fully coupled with chemistry, and secondly, it's very flexible. For example, if someone else discovered a very interesting reaction can occur on aqueous phase, you can add that into the model in no time. So the first study that used this module was in this Wang et al. 2022 paper. So this paper, by the way, if you're interested, if you want to play around with aqueous-phase chemistry, so I have a website on which I have a box model tutorial. Chapter 7 is basically a toy model for the aqueous-phase chemistry that has pH and all the other things you might find interesting. All right, now I would like to talk a little bit more about sulfate. Sulfate has been, so climate scientists have been, the only one piece of chemistry that climate folks are interested in is probably the sulfate chemistry. But in the recent years, we found, okay, there is actually a lot more that we don't know about sulfate chemistry. So Fang et al. So Coming Fang was a postdoc at MIT back then. So he implemented some of the very updated, detailed aqueous-phase chemistry of sulfur into CSM model using the aqueous-phase scheme that I developed. So after that, he found a job in industry, and so after that, I just took over and made up a couple of other updates. So this flow diagram type of thing basically summarizes all the complicated things about sulfur chemistry. We know that the chunk of sulfur is emitted into the atmosphere from the ocean as in the form of DMS. They can undergo different chemical reactions producing different things. And for example, MSA sulfuric acid in the correct places, they can trigger the formation of new particles. And also the sulfate formation happening through clouds and on aerosols would produce lots of sulfate in the aqueous phase to do a lot of other things too. All right, so basically, since I took over, I did a lot of extensive model evaluation using the observations, especially from the atom field campaign. Here I'm showing two examples, sulfate on the left-hand side and HE and PF on the right-hand side. And also I wanted to briefly mention that last year we have a big field campaign called Aroma. We sampled, we had like 4 or 6 flights over the ocean looking at how the ocean emissions of sulfur species interact with marine clouds. And data is being finalized and the modeling analysis will follow. But basically the model is ready for, very much ready for future endeavors. And this basically summarized the roadmap of the sulfur, or the first part of the presentation. Basically, I developed this online air-sea exchange scheme for this CSM model, allowing an improved integration between ocean biogeochemistry and atmospheric chemistry. And I've used this model framework for a couple of things, including ASTAL. And ASTAL turned out to be the most important, most interesting one, because we have observational evidence that points to currently unaccounted sources for reactive carbon in the atmosphere. And organic air was further pointing out that organic aerosols are very likely, very plausible, but they're insufficient to explain all the missing carbon. And lastly, in order to answer some of these questions, we made new model development, allowing us to explore these very exciting new research directions that are summarized in the small diagrams at the bottom. All right, now I'm going to switch gear and talk about wildfires and impacts. So wildfires are a natural phenomena in many of the ecosystems. However, wildfires in populated regions can pose costly risks to human health and properties. So in recent years, with record high heat conditions and severe dry conditions in many of the places, the wildfires have definitely become a growing concern. And if you look at this, is a very interesting paper because it showed that the air quality in many of the places in the United States have been improving in the United States, except for Western United States or the wildfire-prone regions, where in these regions wildfires have potentially offset the decades of air quality gain. This is a pretty big deal. And in addition to that, wildfires have also considerable impacts on weather and climate systems. For example, the smoke injection into, sometimes when the intense smoke wildfires would inject smoke directly into the stratosphere, that will lead to persistent warming in the stratosphere. And also wildfires may also affect the marine ecosystem. Because of the importance that wildfires play in the modern air quality models all have wildfires. However, despite decades of research, it's still very, very challenging to represent wildfires in big models. And there are many reasons. One of the biggest reasons is that the model grids are much bigger than the actual fires, so that the actual physical and chemical processes happening in wildfire plumes, especially in the early stage, cannot be explicitly resolved in coarse grid resolution models. Now you might ask, okay, what's a big deal? What are we missing when running models with coarse resolutions? So studies have shown that the chemical and chemistry and aerosol-based processes like coagulation and condensation, these kind of things, are actually heavily affected by plume dynamics in the early stage. So we don't resolve these things, the chemistry might be affected as well. And in the previous paper that we published using the Large Eddy Simulation model coupled with high-resolution turbulence-resolving Large Eddy Simulation model coupled with chemistry. And one experiment we did, and we showed that even with perfect chemistry and perfect emissions, the impacts of most wildfires on ozone will be biased if the model resolution is too coarse. Now we can ask ourselves, when was the last time when we had perfect chemistry and perfect emission? So these are inevitable biases introduced by coarse resolution models. This definitely calls for higher spatial resolution for chemistry models as well. So if we come to think about it, how do people implement wildfires into big models? I mean, first step, we have to figure out where to place the wildfire source or wildfire emissions, right? So horizontally, it's fairly straightforward. We can just watch the satellite imagery. Oh, there's a fire. We put the fire right there. But vertically, this has turned out to be actually very, very tricky. So this process is usually referred to as plume injection or plume rise. Basically means how high the smoke is being injected into. So here I'm showing the results from the HERS smoke model. So HERS smoke is known as a flagship smoke forecast product. So in the HERS smoke model, the plume rise is calculated using a very widely used plume rise model. It's called Freitas model. So Freitas model is known to have some issues. So I'm showing two examples here. The first example is a sheet fire. In this case, the smoke was heavily affected by very strong near-surface wind, and the model failed to capture the impact of very strong near-surface wind, therefore overestimated the plume injection. If you look at the plume transport there, the plume is kind of transported too far away in the model. The second example is very interesting. This is a Williams-class fire that triggered the formation of a pyrocumulonimbus. That's basically fire-induced thunderstorm. So when this kind of things happens, it would release latent heat that further drives the plume rise. So the model failed to capture that effect, therefore drastically underestimated plume injection. If you look at the plume transport, the plume is completely being transported to the absolutely wrong direction because the smoke is injected into the wrong altitude. So we mentioned before that turbulence scale, high resolution models are required to resolve this kind of plume dynamics and also to understand plume injection. But these kind of models are very expensive and almost impossible to scale up in the near future. On the other hand, in reality, for most of the applications, we're probably stuck with convective scale or mesoscale for most of the applications. And in this kind of model, there's no way that we can resolve the highly dynamical processes happening in the early stage in wildfires. What can we do? The common wisdom, if we can't afford, we can always pretend. So my idea is that we can take the high resolution turbulence-resolving model, use that to train the machine learning, build an emulator, and pretending that we're running the high resolution model in coarse resolution model, inside the coarse resolution models. So when it comes to machine learning, training data set is very, very important. So on this slide, I'm roughly showing how the training data set are constructed. So firstly, I have identified 12 important variables representing the important conditions defining or affecting wildfire plume injections, including stability, wind, moisture, heat, all those kind of things. And then I used Latin hypercube sampling approach to construct a comprehensive data set with about 6,000 unique combinations. And all those things are sent through the LES simulation model, LES model to simulate the plume injection, simulate the plume structure. And then in order to further evaluate, let me go back a little bit. So this is basically the results of almost 6,000 LES simulations, very comprehensive. This is used to train and evaluate the machine learning model. And in order to further evaluate the model, I construct this more realistic testing data set by randomly sample the HERS sounding profile. These are sent through LES sent through LES and generate the fire plume structure as well. And this data set, as you can see, the sample size is a lot smaller, so it's a lot less comprehensive than the other data set. But this data set does carry the advantage of being very realistic. Therefore, it is a more rigorous way to test the machine learning models. Now you might ask me, what does the LES data set look like? So here I'm showing four examples. The first two rows are two examples in the comprehensive training data set. Basically, the LES models are driven by the highly idealized sounding profiles showing on the left-hand side. In the bottom two rows, I'm showing two examples in the comprehensive testing data set. We can see that the LES models in this case are driven by the more realistic sounding profiles as indicated by the black dots showing on the left-hand side. So this is basically the machine learning workflow. I'm not going to dive into the details, but I have tested three very widely used machine learning models. One is random forest, the other is random forest, one gradient boosting, and another neural network. So essentially, the machine learning models take 12 input variables, or in the machine learning world, they call them features, and describing the heat flux, the stability, moisture conditions, and winds, all those kind of things would affect plume rise. And then the machine learning models will spit out three outputs: plume top, plume center, and plume bottom. So this plot basically shows the high-level evaluation using the LES model here as a ground truth. From left to right-hand side, I have the random forest, gradient boosting, neural network, and Freitas model showing on the right-hand side. This Freitas model here is shown as a benchmark model. It's very widely used. We can see that, okay, all three machine learning models, they outperform quite well, and also they outperform the Freitas model. In the second row, it's very interesting because this shows evaluation using a more realistic data set. The key information I can get from the second row is that basically the machine learning model trained by using the fake data also performs quite well on realistic data it had never seen. This is definitely something very promising, and not a lot of machine learning folks are doing this kind of rigorous evaluation, by the way. And the last three rows are basically showing the statistical distribution of plume top, plume center, and plume bottom. And we can see that all the three machine learning models, again, they tend to capture the plume profile shapes reasonably well. But the Freitas model is a parcel-based model. It tends to get the plume top height reasonably well, emphasizing reasonably, but it tends to severely overestimate plume center and plume bottom heights. So you may ask, okay, what is the problem, or what are the issues of the benchmark Freitas model? So there are lots of studies looking into that and trying to improve that, eventually give up trying. And on the right-hand side, I'm showing a couple of very representative examples. In the top row, I'm showing a case in which the plume was heavily affected by very strong near-surface winds, and the Freitas model failed to capture that effect. Therefore, they drastically overestimated plume injection. And the second row is very interesting because this smoke also triggered a major condensation that released latent heat, further driving the plume rise, and the model failed to capture that kind of microphysics interaction. So in this case, underestimated plume injection. The last example is very interesting because in this case, it's kind of a mix between condensation process versus very strong near-surface wind shear. And the Freitas model captured the condensation effect, but failed to balance that with the entrainment induced by the very strong near-surface wind shear. Therefore, drastically overestimated plume injection height. And now in this slide, I'm basically trying to convince you that machine learning models are robust and not overtrained. So overtraining is basically a problem that is for all the machine learning models, or essentially all the regression models. So an overtrained model basically performs exceptionally well on training data set, but very, very badly on new data set it has never seen. So put it nicely, an overtrained model is useless. So here we can actually do a lot of things to ensure that the machine learning models here are actually not trained. And among all the three models tested here, the neural network performs the best. For example, if you look at the result in the top row, which shows the tenfold cross-validation results, it indicates that the neural network shows persistent performance on the new data set it has never seen. In the bottom two rows, I'm basically showing different types of learning curves, and these are basically indicating that the neural network model converges fast, yielding low bias, and also yielding low bias, and these also are important marks that we're trying to hit. There's indicating the performance is quite well. On the other hand, you can see the gradient boosting model is a little bit data hungry, and this is also a minor sign of being undertrained. People often ask, oh, I have 1,000 samples is not enough, or I have 10,000 samples is not enough. There are a couple of things you can do to tell whether you have enough sample or not. In this case, we did experiments demonstrated that for a neural network, the samples is probably comprehensive enough, but for the gradient boosting, simply the model is not able to. It's not as good at learning. The gradient boosting model maybe could use a little bit more training sample. And on this slide, I'm basically showing the model, the results, basically demonstrating that the models are transparent and the results physically make sense. So this small plot here, you can't read the text. I apologize for that. But basically, this ranks the relative importance of all the inputs. The interesting thing is that the three machine learning models tested here, although they are configured and trained very differently, they yield very similar results. For example, all the three machine learning models consistently found that sensible heat flux is one of the most important input. This makes perfect sense with our physics-based understanding that, because sensible heat flux is probably the dominant source of fire-induced buoyancy. And secondly, all the machine learning models consistently found that the surface wind and near-surface wind shear are also very important in affecting the plume injection. This is also consistent with one of the very recent publications indicating that the entrainment that is induced by very strong wind shear, entrainment induced by wind shear plays a quite important role in plume injection. And the ranking here basically shows the relative importance, doesn't tell us anything about anything quantitatively. And this partial dependence analysis really reveals the highly nonlinear feature of the problem. For example, I want to draw attention to this small plot here. I apologize, you can't read the text. Anyway, this plot basically shows that the plume injection is highly sensitive to it's strongly affected by sensible heat flux, but more in the lower range. In the intermediate to higher range, basically the effect plateaus out. It means in that range, other factors start to play a role. If you look at these bottom two rows here, these two indicates that the plume injection is negatively impacted by surface wind and near surface wind shear as well. If you look at the small panel in the middle, it basically shows that in the higher range of moisture levels, some of the models start to pick up the impact of moisture. This is very interesting because moisture itself does not directly affect plume rise, but rather if you take an air parcel with moisture in it, you have to manage to lift it to the condensation level so that it can condense and release latent heat. So the impact of moisture also depends on all the other factors, and the impacts of moisture and microphases are only visible with all the other conditions are kind of right, and what the other conditions are defined, it basically depends on the conditions, all the other things. So this plot basically shows that the importance that the machine learning models are able to find something interesting, something common in this training data set, and they are all quite consistent with our physics-based understanding. So what are the next steps? So up to this point, everything is fairly technical, and I wrote a paper about that, and the paper is currently under review. The next step, we definitely wanted to take a closer look at do a more careful evaluation using ambient observations. So here I'm showing one synthetic example that we got from the Wildfire field campaign. So this is a mosquito fire that we sampled during the Wildfire field campaign. In this case, the smoke was injected all the way up to 14 kilometers, I think. So here we have synthesized 3 sets of satellite-based aerosol and smoke layer high product. They all retrieved using very, very different principles. And in the bottom row, this is very interesting. This is a basic smoke structure that we inferred from the ground-based weather radar. We can see that they're showing some interesting discrepancies, but some of them we can understand from their underlying physics. So in the future, we definitely would like to eventually implement this machine learning-based emulator into 3D models and do more careful evaluation using all the observations. So this project is partially funded by a recent CPO program that I'm a co-leader. I'm a lead PI on it. And here I'm summarizing basically a roadmap here. So wildfire impacts are definitely biased in air quality models or weather climate models with low spatial resolutions. And we found out, plume rise is one very important source of uncertainty. Therefore, in order to better resolve plume rise in coarse resolution models, I developed this machine learning-based emulator trained using the high-resolution turbulence-resolving Large Eddy Simulation model. And this emulator offers improved predictability, which can be used for future applications, for example, simulating multiple satellite products. And with that, I would like to wrap up, and I'll be taking any questions or comments. Thank you very much.
Well, this is a basic question, but if you have all the chemistry right, why are you underestimating ozone in a coarse model? What changes?
So this is the the chemistry is highly nonlinear. If you have higher concentration versus lower concentration of precursors, the 2 important precursors, one is VOC, the other is NOx. In the textbooks they have this ACMA plot showing different ozone formation regimes. With different conditions, the ozone formation efficiency can be very, very different. So it's not a linear response. If you take a let's say air parcel filled with ozone and VOC and stuff like that, and it produces VOCs and NOx, it produces a certain amount of ozone. You dilute that by a factor of 10. The ozone you got is not a factor of 10 lower. It might be more, it might be less. So it really depends on where you are. This This is a highly nonlinear thing about chemistry. And in the models, because models with coarse resolution, anything you injected into the model from point source or small area sources are immediately diluted inside the model grid files. If you look at this plot, it's showing right here. So in the high resolution large eddy simulation model reveals very interesting features, and very close to the fire source, we have seen very strong ozone depletion. This is also verified by the airborne observations. The 1 kilometer model sort of captured that kind of thing, but the 4 kilometer model completely missed that. If you look at the width of the plume, I'm not sure if you can see that. In the high resolution model, it's very narrow. But in the coarse resolution model, it's basically double or triple the width of the model, simply because everything is diluted a lot more faster closer to the fire source. And the chemistry regime is very, very different if you do this kind of simple dilution.
It's funny, Paul, 4 kilometers coarse resolution.
I know.
Because I'm used to dealing with global models. And so just zooming out, I assume these models are going to be run at global scales. That's the idea, is you can have predictions everywhere. Or are they targeted in such a way that you can just, get all this detail in certain parts of the world?
I'm sorry, which model you're referring to?
Well, I'm just thinking of air quality models in general. Like where are we in terms of resolution, and where do we need to be?
Yeah. So great question. So currently in the National Weather Service, they're running the National Air Quality Forecasting thing at about 12 kilometer horizontal resolution. And the HERS smoke model and maybe a couple of other models too are running at 3-ish kilometer over CONUS scale. So 3 kilometer in that world is considered as being very high resolution. Right. And in the 3 kilometer model covering entire CONUS, we cannot afford to run comprehensive chemistry in it. Right. The reason that the National Weather Service running the air quality forecast at 12 kilometers is considering the cost of computational costs. Right. But there are studies indicating that if you're wanting to understand urban air pollution, like decaying of urban emitted NOx or that kind of things, maybe 12 kilometer model is somewhat sufficient, somewhat okay-ish. But to look at, because wildfires, many of the wildfires, they can leave remarkable burn scars as seen from space. But if you look at the active burning areas, they're very, very small. If you're looking at a fire with 1 square kilometer active burning area, that's considered one of the big fires. And with a 3-4 kilometer model, you can possibly resolve that. So, we are not unfamiliar with this kind of issue, like subgrid processing. With subgrid processing, we just have a parameterization or something like that. For wildfires, the plume injection is the one solution that we have for the physical plume injection. For other things, we may have similar approaches. For example, some of the stuff from wildfires are secondarily produced, not emitted from here, but secondarily produced maybe a couple of kilometers downwind. But the coarse resolution models cannot handle that kind of thing, so we might as well emit some of the secondarily produced compounds as primary emissions. From a chemistry perspective, it doesn't make sense, but it's a kind of like an engineered approach to get around before we can get a big supercomputer. So at this point, I think I'm not sure if I answered your question, but basically for air quality, generally speaking, maybe a 12 kilometer-ish resolution is probably fine. But if you want to look at some of the impacts, you want to get down to like 3-4 kilometers. But even 3-4 kilometers to resolve wildfire impact, that appears to be not enough.
Yeah, I may have missed some of this because my hearing is not great, but how do you distinguish in your remote sensing data, your satellite data, how do you distinguish between intense fires, smoldering fires, and how do you, and I'm aware they can do that, but how do you incorporate that into your model?
Great question. I am not there yet. So in the satellite world, they use the smoldering flaming is kind of like a distinct transition, but terminology-wise. But from observation perspective, satellite they use, for example, the FRP, fire radiative power. That's basically continuous. You can draw a line somewhere. Call if the fire-related powers beyond some certain threshold we call as flaming or some other ways. But actually, most of the fires with somewhat with FRP values which are very likely. I shouldn't say that, but it's active area for research. And in the modeling world, there are a couple of ways you can use that information. For example, there are studies using the satellite-derived fire-related power to directly estimate the emissions. So that kind of accounts for the impact of smoldering versus flaming already. So basically, directly connecting the emissions to the satellite fire-related power. We're doing that based on our data collected from one of the field campaigns. But the tricky thing is that we have, for example, in that field campaign, we have pretty good coverage on temperate forest fires, which are very relevant for Western United States. But we also have some observations from the southeast agriculture burning, but we don't have lots of good data for the high latitude regions or Eastern Africa or Australia. So that kind of approach, you're kind of limited by the measurements you have. There are other ways to consider to account for the impact, the discrepancies between smoldering and flaming, which is basically using the bottom-up approach. For example, if for the smoldering fires versus flaming fires, emission factors will be very different. But in the upstream, how do you know whether this fire is flaming or smoldering? That's a very different topic, and there are a bunch of people from a remote sensing perspective. There are lots of people actively working on that. But that's a very big source of uncertainty wildfire modeling that I'm not even there yet.
So can you use the various satellite products for those for vegetation cover for areas of the world where you don't have any specific information?
Exactly, that's exactly what we're doing now. So we are using the relationship that we got from temperate forest fires and scaling that using the observation that we have in common, but scaling that to different vegetation types. That's what we're doing, and we just haven't got a chance to do a full-on test yet. But the model runs, and that's exactly the idea that we're trying to do. Yeah.
Good, thank you.
Can I ask another question, just to follow up, because you mentioned urban, and you said you thought 12 kilometers is a good, is sufficient for urban. But I think, a lot of what I've seen about urban air quality is that there is a lot of heterogeneity within urban environments. And, maybe there's not, I don't know anything about chemistry or, but it doesn't seem like this type of approach wouldn't work because you have such a distributed set of sources that are, how would you handle that?
Great question. I might have said a little bit too much about that because the 12-kilometer thing is, previous studies indicating that if you wanted to look at, for example, decay of NOx, that kind of thing, is a typical urban type of pollution. 12 kilometers is the least you can, the least you should go. Higher resolution, definitely you would expect a higher, you can better resolve some of the stuff.
Okay.
I do agree with you that some of the stuff that we see, 12 kilometer-ish resolution might not be enough. For example, looking at the winter air pollution in Utah Valley, that kind of places, you definitely, or to resolve some of the weird meteorology in the Rockies, you definitely need higher resolution to be able to resolve that kind of stuff. And for that kind of applications, definitely 12 kilometers is probably not enough. And if you're talking about urban heterogeneity, like places with very high-rise buildings, the chemistry heterogeneity and the interactions with the building, with the flow and that kind of stuff, maybe even 3 kilometers is not enough. So in our group, there are colleagues out there as well. They're trying to develop this urban canopy model that basically better resolve the interactions between the urban and the atmosphere with a focus on atmosphere chemistry and air quality. But essentially, the computational concern is a real one. So balancing everything, I guess National Weather Service decided we're going to stick with 12 kilometers for now. But in the future, we could use higher spatial resolution as well.
Yeah, this is an interesting, interim solution.
Definitely.
Can I ask you, going back to the first half of your talk, this missing active carbon, these short lifetime species, do they have an importance to them, or are they just an interesting puzzle that we're an order of magnitude off? Nobody likes to be an order of magnitude off, but other than the processes in their own chain of life, does it have broader implications for
Right.
errors that matter in other ways?
Right. So, great question. Yeah. So, the potentially missing reactive carbon pool in the atmosphere may have broader implications. For example, it might perturb the oxidative capacity of the atmosphere. That would affect a whole bunch of things like methane removal or that kind of things. And combining with the ocean emission of other things, like potentially reactive nitrogen species, another potential area to look at is that much of this might be influenced by modern day anthropogenic emissions. Back into, for example, like if we look at pre-industrial period, back then we didn't have lots of cars or factories emitting all those things, and the oxidative capacity back then might be very different. Therefore, the ozone formation back then might be very different, and we don't have lots of good ozone measurements back in pre-industrial periods. But if you run the models with and without all those potential sources or mechanisms perturbing ozone, with and without, you're seeing a decent decent change in ozone. That would potentially change the radiative force, the baseline of the ozone radiative force. So potentially may have some impacts, but we just don't know. I mean, look at the numbers, it's a small number, but this covers much of the remote ocean, which is again covers 70% of the surface of Earth. So statistics speaking, I would say it might do something collectively. Yeah. So I don't have a clear answer, but I'm guessing it might do something. Yeah. And we're looking into trying to find other evidence from ice core, from isotope, looking at indirect evidence to support whether things are really off or that kind of stuff. Isotope is a really stark magic. It's tricky to interpret the results, and sometimes we're seeing very promising things, and then experts warn us, okay, there are other ways could yield this kind of results too. So we're still trying to figure out. Yeah.
Now it's partly a science puzzle.
Yeah, definitely.
Yeah.
But so far, I'm glad that we can successfully rule out some of the possibilities. It's one step at a time, I guess. I'm not sure if we have questions or comments
Any
online.
questions online, Ryan?
Nothing, no.
Okay. All right. Thank you so much. It was really great hearing all about this exciting.
Thank you so much.